Today's topic is going to be the rational root theorem, but before we get started on the actual theorem, I want to talk about a couple of sets of instructions. First we have solve by factoring, and we have an equation here, x to the fifth plus 3x to the fourth minus 4x cubed minus 12x squared equals 0. And then we have the instructions to identify the x-intercepts by factoring, and we have f of x equals x to the fifth plus 3x to the fourth minus 4x cubed minus 12x squared. And I want you to know that these instructions mean the same thing. So let's go through and find these x-intercepts by factoring. When we do that, our first step is actually to set 0 equal to y. So we're going to replace f of x with 0, and then we have the exact same equation as I have written on the left-hand side of the page over here to solve by factoring. The next step is going to be to actually start factoring. First step in factoring is to look for a greatest common factor. All of these terms have at least two x's, so our greatest common factor will be x squared. So I'll rewrite this as 0 equals x squared times x cubed plus 3x squared minus 4x minus 12. And then I'm going to factor what remains in this set of parentheses. And since there are 4 terms, I will factor by grouping. So I'll look at my first group here and second group. In the first group, the greatest common factor is x squared again. So I will rewrite my equation 0 equals the x squared that I had when I started, and then I'm going to take the x squared out of my first group, so x squared times x plus 3. And then I need to take out something from my second group that will make it match x plus 3. And the number that's going to make that happen is a negative 4. So I'll have minus 4 times x plus 3. Then I can rewrite as 0 equals the x squared that I had before times my common parenthesis of x plus 3 times the common factors that were left outside, x squared minus 4. Now I'm still not done factoring because I have an x squared in here. This x squared minus 4 happens to be a difference of squares. So I'll go another step in factoring. 0 equals x squared times x plus 3, and then I'll factor x squared minus 4 into x plus 2 times x minus 2. And now I have this whole thing completely factored, and that is going to give me a set of x-intercepts. This one is x equals 0, and that has a multiplicity of 2, and then x equals negative 3, x equals negative 2, and x equals 2. So you can see that when I started with my original function, it had a degree of 5. And when you look at all of my roots, I have 1, 2, 3, and then 2 more here for 4 and 5. So when my degree equaled 5, my number of roots, or x-intercepts, also equals 5. So I've found them all. Now another thing that I want to remind you of is that when I find an x-intercept, such as, well, we could take any of these. Let's just look at x minus 3. Remember that when I find an x-intercept of negative 3, and I work that through using synthetic division, remembering to use placeholders for the x term and the constant term that are missing. Oops, I don't need a plus there. What happens when I have identified an x-intercept, bring that 1 down, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. What happens is that the remainder equals 0. And when the remainder equals 0, that tells me that I found an x-intercept. So when the remainder equals 0, we have identified an x-intercept. So another way to find x-intercepts, besides just factoring, would be to just guess a number, try synthetic division, and see if we get a remainder. So let's write that down. We could use guess and check to find x-intercepts. And what that would look like would be we would guess a number, do synthetic division, and then see, is the remainder equal to 0? If so, it's an x-intercept. If not, guess again. And we could just keep repeating and repeating and repeating that process. But that would take forever because there's just an infinite number of values that we could choose as our guess. So what I want to show you is that there is a way to list likely candidates for x-intercepts. And that's by using this possible rational roots. Possible rational roots. And remember that rational means a number that can be written as a fraction. So this will not locate or find irrational roots like the square root of 3 or imaginary roots such as 2 plus 3i. So these possible rational roots, they'll find any that would be rational, but they won't find the irrational or imaginary. So here's how we find our possible rational roots. We are going to list factors of the constant term over a list of factors of the leading coefficient. And then we will split the list. And I'll show you what I mean by that because that's not very descriptive. But you'll know what I mean once you see it happen once. So if we go back to our original problem, our problem was f of x equals x to the 5th plus 3x to the 4th minus 4x cubed minus 12x squared. Well, on this one, the constant term, the one with no variable, is 0. And the leading coefficient is 1. So our possible rational roots would be the factors of 0, which are really 0, over the leading coefficient 1. So this would only give us possibilities of 0. So let's look at an example that does not just have 0 for a constant term. So f of x equals 2x cubed plus 6x squared minus x minus 30. Now in this problem, 30 is our constant term. We don't need to worry about the negative. And 2 is our leading coefficient. So when we list the factors of 30, factors of 30 mean the numbers that could possible rational roots. Wow. I'm having some spelling problems right now. Hold that thought. Okay, possible rational roots. When we list the factors of 30, numbers that could multiply to give me 30 are 1 and 30. And remember that to get negative 30, it could be positive 1 times negative 30 or negative 1 times positive 30. So for each factor, we're just going to write plus or minus. So plus or minus 1 and plus or minus 30. And then plus or minus 2, and that's times 15. Plus or minus 3 times 10. And plus or minus 5 times 6. So all of my possible factors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30. And then I'm going to put that over the possible factors of 2. So plus or minus 1 and plus or minus 2. Then when I split the list, what I'm going to do is basically I'm going to cover up all the numbers except for 1 at a time in my denominator. And I'm going to write these all as fractions basically. So my list will include 1 over 1, 2 over 1, 3 over 1, 5 over 1, 6 over 1, 10 over 1, 15 over 1, and 30 over 1. So you can always just start out by listing all of your numerator values because they're always going to be in our list. And then we're going to cover up the 1, and I'll write plus or minus 1 over 2, so that's going to give me 1/2. And then 2 over 2 would be 1, which is already on my list, so I won't write it again. And then 3 over 2. And then 5 over 2. And then 6 over 2 would be the same as 3, so I won't list that again. 10 over 2 would be the same as 5. 15 over 2 needs to go on our list. 30 over 2 would be 15, so that's the end of my list. So that's how you split the list, is you write each of your numerators over each of your denominators. Don't repeat any values that are already there. And then that would be these are the only possibilities for rational roots for this particular function. So there would be no point in me testing out, say, -7 because it's not in my list of possible rational roots. On the next video, we're going to look at how to use this list to identify all of the x-intercepts for a function.